Okay, take it away, Patrick.
Okay, so welcome to the first of two talks I'm going to be giving. This time round, building on my previous two talks, sort of talking about the category of sheaves and the category of presheaves. These two will be talking about the topos structure that is on both categories. So the main goal of these two talks is to prove that the category of sheaves on a site forms a topos, hence the title, and that will be broken up into two talks. So this one I'll be showing that the category of presheaves, just on an arbitrary small category, forms a topos. Second half of this talk I'll be describing the sheafification of or associated sheaf functor of a presheaf. So this is a way to take a presheaf and canonically upgrade it to get an actual sheaf. This is useful sort of in two fronts. So one side, when we're doing geometry, a lot of constructions that we want to do, taking tensor products, quotients, won't give us a sheaf when we feed in sheaves. They'll give us a tensor product of two sheaves as a presheaf. So we can sort of get a sheaf back, which is good. The other way around is that we can understand the category of presheaves quite easily, but the category of sheaves has sort of fairly opaque structure until we know how to compare it. And so this universal sheafification functor acts as sort of like a comparison tool. And we'll see how useful that is next talk. Okay, so to show that presheaves form a topos, well, first I'll introduce some notations. So C being a small category. And we'll write PSHC for the category of presheaves, so for the presheaves and sets. So to show that this is a topos, we need three things. We need all small colimits and limits. We need a subobject classifier. And we need exponentials. So this will be the focus of the first half of this talk. So to kick things off fairly easily, so we will recall that the category of sets has all small colimits and small limits. That's just a fact from basic category theory. I'll assume that's known. So we can actually use that straight away to define small limits and small colimits of presheaves. Basically, if we've got a system, so we've got a system Fi presheaves, then we just define the colimit Fi as C. So C is going to be in our category, which is going to define that to be the colimit in sets. And similarly for limit, so limit Fi at C is the limit in sets. Okay, so this is a fairly basic construction, but it allows us to do sort of everything that we want to do. Moving on. All right, so that ticks off our first little requirement. So in particular, of course, that means we're going to have products, we're going to have pullbacks, push forwards, that sort of thing. Okay, so we should think of a colimit in sort of presheaves as a family of colimits and sets. Mm-hmm. Okay, so that's done. So subobject classifier, it's a little bit more complicated. Now, we'll recall from a few talks ago that there is a bijection. We have a bijection, so subobjects of HC. So this is some representable functor. If we recall, HC of D was Hom D into C. That is in one-to-one correspondence with sieves on the object C, where a sieve was a set of morphisms F into C closed under precomposition. Okay. So we want our sub-object classifier to satisfy. We want some omega such that hom from F to omega, so HC to omega is going to be omega of C. This is what this is satisfier. So this is the canonical choice that we're led to. It's true.
You mean the right hand side, you want sieves?
Yes, sorry. So where's your base?
Good question. There's a pile of potentially very gross ones over here. Yeah, I don't know.
So this is what we're looking for in a sub-object classifier. So, using this, we're going to go ahead and just define so we just set omega of C to be the set of sieves on C. Now actually this is not just a function on the objects of the category, but it is actually a presheaf in that if we have F from C to D, then we define omega of F to be what I write as omega F of S to be S restricted along F, which is just going to be all those morphisms H such that F after H is in S. Okay, so this is a pullback sieves along morphisms. Okay, so now we have a legitimate presheaf, and I'm going to claim that this presheaf is a sub-object classifier. So first, what we really need is some morphism from the terminal object of presheaves. So we'll just recall that the terminal object is defined by 1 of C is the point set for all objects C. So we define our natural transformation true from 1 to omega, kind of the only way that we can. So we define it on objects by sending the point between the Maxwell sieve. So this is the set of all morphisms that go into C. This is our only canonical choice here. So the claim I'm going to prove next is that this is actually a sub-object classifier. So I'll put this into a lemma. So I'm going to claim the monomorphism true, I've just defined, is a sub-object classifier. In presheaves. Okay. So just to begin our proof, I'm just going to give a little sketch of what the picture is in this sort of situation. So we're going to have, suppose we have a pair of presheaves where G is a subsheaf of F. This means that on every object, G of that object is inside F of that object. Then if we have a morphism say f from C to D in our category, then f is going to define, by restriction, by the sheaf condition, presheaves condition, going to define a morphism from f of D to f of C, which will take some object element x to x restricted along f. And this may or may not land inside G of C. Just going to point out this notation here, x with restriction along f. This is not standard as far as I'm aware. McLean and Mordyke use x dot f.
Yeah, it's also common.
Okay, I'm not saying this, but
Just to be clear, this is notation for curly f or little f of x.
yeah, so. It's much shorter than writing the other way around. So this may or may not land inside G. So what we want then is for our sub-object classifier to sort of pick out sub-objects. So it has to sort of know when something lands inside G of C, when it sort of pulls around. So to do this, so given x in f of D, we're going to define an analog of sort of a characteristic function for sets. This is going to be defined by, this is going to be some sieve that lives on D, which will be phi D of x. What's that going to be? It's going to be all morphisms which land in D, such that x restricted along those is in lands in G. Okay. So this is certainly a sieve on D. It's a fairly quick check. And in fact, it's natural with respect to D. So then this defines a natural transformation phi going from f onto omega. All right. So the next question we can kind of ask ourselves is, when is phi d of x going to be the maximal sieve? Well, so if phi of d of x is the maximal sieve, that means that every morphism into D pulls x, well, along that x pulls back into G. In other words, that means that x was in G all along. So to rephrase that, we have that phi d of x is equal to t of D if and only if x is in G of D. Or, in other words, we have a pullback diagram, G down to F, across to the final object, like this. So to rephrase, I've said that x was going to be, so x that's come from f of D actually came from G, if and only if going around this way lands you in the maximal sieve, which is what going around this way does. So this really is a pullback. All right, but then to be a sub-object classifier, we need this phi to be unique. That's the last little thing I need to show in this proof. All right. So the last thing I had to show was that phi was unique. So take omega theta from f into omega, also fitting into that pullback. Wanted to show that this theta is equal to phi. So if we take f from C to D once again, and x is going to be in f of D, then the pullback condition, just as we've said, means that x restricted along f is going to be in G of C, if and only if phi c of x restricted along f is equal to t of c. But then, because this phi is natural, this is equal to phi c of x restricted along f. Now with this is a presheaf structure on sieves. And this then means that because this is in here, if and only if so theta c x also holds. So this means that phi c of x restricted along f is equal to theta cx restricted along f for all f x as above. But because this holds in this generality, this just means that phi is equal to theta. So this shows that this theta that we've defined, so initially only using representable presheaves, and just extending the idea of classification up to general presheaves, is in fact a subobject classifier. Okay. So now we've made some pretty good progress. We've got limits, small limits and co-limits on presheaves, and we've got ourselves a subobject classifier. The last ingredient for this to be a topos is that we need exponentials. So, as I said before with the limits and the co-limits, in the special cases of product, we have f and g presheaves. The product of those two is just the object-wise product. Now, to find an exponential, we want to find a right adjoint to the functor right, so we want our exponential to satisfy this property. It's going to be a right adjoint. So our sort of initial thing is to say, well, we know from other categories with sort of these types of adjoints that maybe we could just use HOMs. Right? So naively we might say, hopefully we could just take HOM, take a exponential of g with f at c to just be HOM of f of c, g of c. This is certainly my first sort of thought. But of course this is actually really stupid because this isn't actually a presheaf at all in any proper way. There's no way to sort of do morphisms properly. So we have to scrap this idea. All right, so then how are we actually going to define exponentials in this category? Well, the only thing we can actually go on is this adjoint sort of condition, the definition of what the exponential has to be. So we know, okay, so to define our exponential object, the only thing we can actually use is the adjoint property that we know. So we know that if we have a presheaf H, then we need that hom of h times f into g has got to be in bijection with hom h into this exponential of g with f. Okay, so where does this get us? Well, using Uniqueness, we might want to take h to be representable presheaf for some c. What this means then is that gf of c, which is forced to be hom hc of this exponential, has to be in bijection with hom hc times f into g. Right, so this is what we can get from this adjoint condition. Now this on the far right hand side has, so obviously this we can't use because this mentions the exponential object. This is no definition. On the right hand side though, we actually just have some objects totally independent of whatever this exponential is meant to be. So we can do the so-called French trick and take this property of things just to be the definition. We just define this to be the case. So explicitly, an object in the exponential over C is some natural transformation from the product of presheaves, the representable presheaf, and F into G. All right. So we'd better actually show that this isn't, just sort of madness pushing around symbols.
I mean, the idea, right, is that if it exists, it has to be this.
Yes.
So you just now have to check that it actually exists.
Yep. So it's that's what will be the content of this next lemma. Oh, I should remark as well that this is the presheaf on C. So this is going to obviously takes us to the set of all natural transformations that lands in sets, and then given a morphism from C to D, the transition function, the induced function on sets is going to come from this representable functor. And if you sort of write this down, you'll see everything works and goes in the right direction. Just sort of stress that. Okay. So the presheaf GF above is So what we're going to do is we're going to actually prove that this adjoint condition holds. In order to do that, we're going to use one of the many standard characterizations of adjoint functors. So to begin, we're going to write down.
You were writing PSH before, now you're writing proof.
Thanks. So we're going to write down an evaluation map. E is going to go from exponential times F into G. What's this going to do? Well, for objects C and natural transformations for natural transformation theta, and for some element y in f of c, E of EC of theta y is going to be theta c of the identity at c and y. And that's going to be an object landing in G of C. Okay? So this is going to evaluate a natural transformation at this guy here. Okay. So the claim is that to any natural transformation phi from h times f into g, there exists a natural transformation unique natural transformation, thank you Dan, phi prime from h to this exponential, making the following triangle commute. Okay, so this claim will, by one of the characterizations of adjoint functors, prove that this is, in fact, the exponential object that we need. Okay, so to prove this claim, we need to write down phi prime. To make this diagram commute. So we're going to define for object C and some object U in HC, we're going to define phi prime C of U at D. Of course, phi prime C has to land in this, this set of functors. So evaluated at D is going to be some functor from
We evaluated these, but phi prime CU is something in G to the F to C.
yeah, and that's going to be a natural transformation from HC times F into G.
HC times F into G.
Yeah.
Oh, okay, I see.
And then that is that natural transformation at D.
I see.
Yeah. Okay, so this is going to be this morphism here. Explicitly, we're going to take F and X, and we're going to send them to phi D, while U restricted along F and X. Right. So what remains is to check that this works. So this is fairly easy to show that this is natural. I'll leave that to you guys. And then using the definition of our evaluation, we have that E at C of phi prime C of U with Y is equal to prime C at U C, 1C Y, which is equal to phi C of U Y. This triangle does indeed commute. Now, in the interest of time, I'm going to leave the uniqueness part of this proof as an exercise. I also encourage you to sit down and write down all of these details, because this is really, really symbol heavy. I know it took me a little while to sort of see what exactly was happening. But the point is that we do indeed know that this exponential exists. So then the theorem, we've proven putting all this together, if C is a small category, then category of presheaves on C is a topos, which is what I've been claiming for the last few talks. Okay, so now that we've got that on the way, what we really want out of these two talks is to show that the category of sheaves on some site is a topos. So the way we need to do that is we want some way to compare the categories of presheaves and the category of sheaves in sort of a universal kind of way. That is going to be done using sheavification. Okay, so what do we want from some sort of sheavification process? We want to take f presheaf, and we want some sort of function a, and it's going to take f to f with a hat, and this had better be a sheaf. And we'd also like that, given any morphism, f to some other sheaf, g, we'd like that this factors through. So we not only want to be able to upgrade f to a sheaf, we'd like this to be universal amongst morphisms into sheaves. For technical reasons, we'd also like this to preserve finite limits. So the construction we're going to give today is called the plus construction. And it is a way of doing this. Okay. So to proceed, we're going to need yet another sort of definition of a sheaf on a site. I'll offer some explanation after I give it to you. So take a site C with the Grothendieck topology tau, F presheaf, and C an object, and S some covering sieve of C. Then a matching family for S elements of F is going to be a function assigning to F from D to C in S an element XF in F of D such that XF restricted along G is equal to XF precomposed with G whenever the composition makes sense. And an amalgamation of a matching family is some object x in f of c such that x restricted of f is xf. For all f in S. Okay, so how does this relate back to the definition of sheaves I gave previously? Well, from the topological picture, a matching family, say if we were on this site, was coming from a topological space. A matching family is exactly the same thing as a collection of sections over elements of an open cover which agree on intersections. Because of course this requirement here, that so the section over that particular open set being restricted to a smaller one being the same as the one off that smaller one, means that they agree on intersections. Okay, then an amalgamation for a matching family is a way to find a global section from which all of these local sections appear as the restriction. So this is sort of how we sort of see the sheaf condition sort of appearing from a topological space. From our definition that we gave in my second talk, we just have to observe that a matching family is just a natural transformation from S to S. And an amalgamation is a natural transformation from HC into F, which of course by Unada is just some section. And the requirement that this restriction requirement amounts to the fact that means that the inclusion of S into HC, so that this natural transformation here, amalgamating implies that S into F lifts to HC into F uniquely, i.e. right. So then we see that we get a new definition of a sheaf on the site being a presheaf such that every matching family has a unique amalgamation. And this is how this sort of definition I've given here ties in with sheaves as we've been sort of talking about them so far. All right. Well, why have I actually just given you a new way of saying something that we kind of already laboured our way through? Well, this way of sort of talking about matching families and amalgamations in terms of sort of presheaves and sheaves on a site makes it much easier to sort of see how we're going to construct a sheaf out of a presheaf. For instance, firstly, we can straight away see that the only obstruction to a presheaf being a sheaf is A, that not every matching family has an amalgamation, and B, that amalgamations aren't unique. So the first problem is sort of harder conceptually to think about. So to get from a presheaf to a sheaf, you're going to want to attach amalgamations. But the second one you can kind of conceptually really easily think about. We want to crush away excess amalgamations. The way we do that then, using the magic of category theory, is via this definition. So with F being a presheaf on some site, we define F plus at C. And bear with me for a moment here. This is going to be the co-limit over all covering families of C of the set of matching families of S with F. So explicitly, an object in this guy, where this colimit is taken under the reverse ordering of these covering sieves. All right. This doesn't mean a huge amount the first time you see it, but don't get too scared, because this actually really captures exactly what I was saying about kind of modding out by excess amalgamations. So if we unwind this, an element in here is going to be some family bold X of these sections. So each xf is inside f of d, and we're requiring that xf restrict along k is xfk. Whenever this makes sense. Now the colimit induces an equivalence relation on this set of matching families. So explicitly, equivalent to some other one y, yh, in some other matching family. They're going to be equivalent if there exists some common refinement T in both R and S, where T has got to be a covering sieve, and X H be equal to YH for all H in T. So in words, what this means is that we take two matching families, this X and this Y. They're going to be equivalent. These are indexed by covering sieves. These are, we're going to say declare them equivalent if there is some sub-covering sieve of each of these two covering sieves, such that the sections indexed by that sub-covering sieve match across the two, i.e. like they kind of agree on the intersection. So, okay. Now it's not hard to check that F plus C is actually going to be a presheaf. So so if we have at this stage we only have a function taking objects of C to a set. If we have some H from D to C, then we define restriction xf restrict along H is just going to be x H f prime, where now f prime is in the pullback of S. So not only do we have a function on objects, but we actually have sort of a bona fide presheaf for f plus. Not only do we have that, but we have a sort of canonical map from f into f plus. So eta going from f to f plus. What's that going to do? Well, eta c of some section is going to just be sent to all of the restrictions of that section to along functions in the maximal sieve. Okay, and it's pretty easy to check that this lands in F plus. All right, so where does this take us in our little sort of attempt to define a canonical way of building a sheaf out of a presheaf? Well, unfortunately, F plus won't be a sheaf in general. It is, though, what is called a separated presheaf. So if is presheaf on the site, then F plus is separated, i.e. all matching families have at most one amalgamation. I won't prove that here. You can find it in Grothendieck. It's not a particularly technically revealing proof, but it's interesting to read. Okay, so the reason that we kind of believe this is true, going back to connecting to the motivation, is that this equivalence relation crushes any sort of multiple amalgamations into the one. You can sort of check that on a toy case, if you like. All right, well, so it doesn't seem like we've got very far. We've got a sort of a way to take a presheaf to get a separated presheaf, but this doesn't seem to address the issue of having to have more amalgamations, sort of attaching more amalgamations that we don't get. This is where like the next theorem is particularly amazing. So amazing theorem. If F is separated, then F plus is a sheaf. I'm also not going to prove that, but this is amazing. So we've taken a thing that a priori doesn't seem to do much other than mod out by excess amalgamations, but actually when you apply it twice, you get the actual more amalgamation, you get the extra sections, extra amalgamations that you need. So this is really cool. Okay, so now we've achieved our goal of upgrading a presheaf to a sheaf, and it's functorial. What we need next is to show that it is universal.
So explicitly, F goes to F plus plus, which we haven't quite seen.
Sure. So our desired sheafification is F maps to F plus plus. So the next result is going to show that this is universal, actually slightly stronger than we need it to be to show that it's universal. So if G is a sheaf, outside, and F a presheaf, then any morphism phi from F to G factors as F through this eta going to F plus uniquely through here. So it's going to factor through the F plus, so this separated presheaf. So in particular, this lemma means that if we applying this lemma twice, means that any morphism from a presheaf to a sheaf factors through this sheafification. And the proof of this lemma is some nice practice. We're working with this plus construction. So an element of F plus of C is going to be a matching family. For some covering S of C. And we know that for any H from D to C in S, nd of xh is going to be equal to xh restricted along k, k in td. Now by the matching property, we also know that xf f in s restricted itself along h is xh f bar in h star of s. But then because h was inside f, h star of s is equal to t of d, maximal sieve. So we know that f in s restricted along h is just going to be nd of xh, where d is the domain. Okay. Okay, so what do we know at this point? So we know that e to d of xh, for some h in s, is just going to be equal to the restriction of this matching family along h. So if we want this phi prime to exist, it had better map this guy, this matching family, to the element y in G and C with y restricted to f, which is of course equal to phi prime of x restricted to f, which by naturality is equal to phi prime of x restricted to f, which is, then we know, phi of x f. And so it will take place for all f in S. This is what we require to be true of phi prime. But then G is a sheaf. So the matching family consisting of all these phi's of xf, f in S. This is our matching family with respect to G. This amalgamates uniquely to the desired element y. So we're done. This phi prime exists. It maps the matching family to the y with this property, and we're done. So this is kind of, I recommend that you go back and sort of check the details of this lemma too, because this is sort of the best exercise in understanding the definition of the plus construction and also understanding the definition of the sheaf condition in terms of matching families. All right, so with all of this put together, what do we have? We have our final theorem. It goes like this. The inclusion functor, iota from Sheaves on C to presheaves on C has a left adjoint A which preserves finite limits. Okay. So with what we have so far, it's not hard to prove this. So first, obviously, clearly, A of f being f plus is well defined, as in it lands in the category of sheaves. And the adjointness comes from the fact that the adjoint property follows because f going on eta to f plus going along eta f plus to f plus is universal by our previous lemma. And so it is the unit of the left adjoint. Okay? So what really we need to show, the detail that might be a little bit surprising, or not so obvious based on what we've done, is our last claim that this left adjoint actually preserves finite limits.
Particularly it's not for free just because it's an adjoint.
No. So for free, we know that the sheaf category, based on this, already we have a lot. So based on this, the sheaf category we now know has all small co-limits, which is going to be useful, showing that it's a topos. This shows it also has finite limits, which is nice. So as I mentioned before, the matching families are the same as natural transformations from S into F. So in other words, we know that this thing match SF is in bijection with SF. And we also know, so I'm going to use a couple of facts. These are basic facts from category theory. It's the fact that HOM the HOM preserves.
First time I looked, I saw two HOMs.
So we know that HOM preserves all limits, and two filtered co-limits commute with finite limits. The second one is really the crucial point. This means, so putting these two together, that for finite some finite index category, we're going to have the limit of the fi plus of that. It's going to suffice to show that 1 plus works because we can apply the plus the second time. What's that going to be? By definition of the plus construction, that's the co-limit of covering sieves of this HOM set. HOM commutes with the limit, so that's isomorphic to this. But then, because of the second fact, this is isomorphic to switch down limit and co-limit, and then this, by definition of this guy, is equal to yes. 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 This shows, this shows that taking finite limits of presheaves and then applying the plus construction, that is the same as applying the plus construction and then taking a finite limit. All right. So now we've shown in this talk that presheaves form a topos, and we've also shown that we have a canonical way, the associated sheaf or sheafification functor, which takes a presheaf to a sheaf that's the left adjoint to the inclusion functor, and that this guy actually even preserves finite limits. So next week, I'm going to come back and use all of this to show that the category of sheaves on some site is also a topos. Thank you for listening.